All right, let's go. So we are back today. Did you guys know there's only, including today, 3 lectures left for class, right? There's class today. There's class next Wednesday because Monday's a holiday, Marathon Monday. And then, anybody running the marathon? Somebody is. I know somebody in the class is, but I don't remember who it is. Anyway, and then next Wednesday we have class, and then the following Monday we have class. Labs next week will be only Tuesday and then the following Monday. We're not actually going to do a lab. What we're going to do is, one, work on your, or do the class evaluations, and then I'm also going to help you guys out with the projects. Okay, so it'll work out just fine.
Wait, this is lab next week?
Lab next week, yeah. Yeah. You probably don't need to, well, you need to go to fill out the evaluation. That's it, yeah.
So then if you're on the Monday lab, you'd have to wait another week?
If you're on the Monday lab, you have to wait the other week, yeah. Which begs the question, right?
How would we get help on our Monday lab?
Well, it begs the question about when the due date's going to be, right? So we may do a little extending on that, but I've not made that decision yet, which means don't stop working. Okay? So, but I will probably do something along. There's enough. I've kind of seen enough of you guys work, and you are doing great ideas. I think it may take a little longer for some people to get enough code done to get the project done. But we'll talk about that. But the point is, next week's lab will not be a lab, and Monday there isn't any class. So that's that. The other bigger point was that there's only 3 classes left. The last class on the final Monday is going to be a review, kind of like what we did for the mid-year. I'm going to go kind of review everything, give you kind of pointers on what to study, etc. But next Wednesday's class, I'm still trying to decide what to do. How many of you are either next year or at some time in your future taking Comp 40? Like almost all, most of you guys. The other ones are snickering right now saying, ha ha, crazy people. Here's what I was thinking would be a good idea for Wednesday's class. I think it might be a good idea to say, here's some of the things you might need to know for Comp 40. Like this is how C is different. This is what it means to have bitwise operations on individual bits. This is some more things. I'm going to ask various people in 40 now to weigh in on that. And then we'll do that, so it'll be a little bit like that. And then I'll give some, what I would do over the summer to prepare for Comp 40 sort of thing. Does that make sense? I think people might like something like that. I'll probably do that, and it won't be other data. The other idea is to do some other data structure, like a red-black tree or something that we haven't talked about yet. But I think I don't want to test you on that stuff. You guys are all going to be super crazy next week, busy anyway. So I'd rather have the last testable stuff be kind of maybe more or less today, really. And even some of today is not really testable. So I think we've covered the stuff that I wanted to cover by now. Let's put it that way. OK, so I'll probably do that with the Comp 40 stuff. Questions before we actually get going? Anything else? OK, here's what we're doing today. We are going to talk about some very related topics, but we're going to basically talk about this thing called a vector, which is a dynamic array where all the details, the ugly details of expanding and keeping track of the expansion and the capacity and all that is handled completely for you. So to use an array, it's like super easy, and a lot of the stuff that you have to worry about when we're doing dynamic stuff not necessary for the vectors. So that's good news. The reason we're talking about that, number one, is because I think you'll find it useful for your project, for the song search. Okay. Number two, it ties directly into this idea of templates, which are the way vectors and the other containers that we've talked about, like queues and stacks, actually work under the covers. So we're going to go into some details of that too. OK? We'll do that. All right, first things first. So when we use a vector, or when we use a queue, or when we use a stack, like we did in lab this week, it's called a container, and it is part of the standard template library. And here's a little motivation for why we care about this whole standard template library. Think about how, in real life, how we take a container and what kinds of things we can put in that container, right? If you have a shipping container like this, Okay. By the way, the guy who invented this shipping container in like the 50s, it's like made like probably billions of dollars in 50s money, because it works on ships, and then you transfer it to trucks, and it works on whatever. It's in trains and all. That's very cool. But anyway, shipping container can hold lots of different stuff. Shipping containers are generic containers to hold things. They can hold toys, they can hold auto parts, whatever. You can have containers that store specific things, right? I think Apple Computer, in the way they package their stuff to ship to you, is a great example, right? Have you ever opened up like a computer, like an Apple computer, or like the iPhone, and the boxes, everything's perfectly aligned, and the phone sits right in there perfectly, and it's perfectly engineered for an iPhone. Like no other object will actually work in it. Yeah. It is an array list. It's basically the same. Well, yeah, it's basically the same thing as an array list in Java. Yep, absolutely. But so as far as the containers go, you do have these specific ones. Another one that I like to use as an example is, you guys know deviled eggs, right? Like delicious, right? And you can get ever seen those plates that like they have like spots for deviled eggs in there, and they've got like 10 spots or 12 spots or whatever, and there's your and you pass it around. Well, that plate is not made for anything but deviled eggs, right? There's nothing else that's really going to fit in there. I suppose you could make ice cubes in it or something, which would be kind of cool, like half egg size like ice cubes. But other than that, like it's not really going to maybe M&Ms or something. But you can't really. It's not really made for that. Made for one thing. Containers in general, we like them to be able to hold lots of different things, because then you can utilize them for lots of different things. And if you invent this sort of thing, you make millions of dollars, right? Well, containers can also hold cute little kittens, right? There was a stowaway cat found in a shipping container. This does not look like a happy cat. He's not a happy cat, right? He just spent 3 weeks like rolling around the open seas, having no idea what was going on. But anyway, but the point is we want these containers to hold lots of different things. Okay, this is the motivation for the standard template library. The ultimate goal for the library is to hold any kind of object you can think of in a type of container. So if you want to store strings, you can store strings. If you want to store floating point values or integers or structures of things or classes of things, you can store those in these containers. And you have to be able to build them such that they are generic enough to hold that. Okay, so that's kind of the point. If we want a queue of floats, we use floats. If we want a queue of integers, we use integers. Some languages, Java used to be this way, but they've kind of gone away from it, allow you to store multiple things in one container, right? That's not really what we're talking about here. We're talking about pick a type of object, store lots of those type of objects, but any individual object of that type will go in that container. That's what we're talking about here. Okay? And we need to be able to do that. In fact, this is built into a number of different languages. Java, Python is kind of similar to that. Some of the other languages, Scheme has some of this ability as well. And so this is not a like specific to C++. We've already seen a couple of these. I've mentioned them a few times already. We've seen queues and stacks. Okay, we have been storing integers in them, but we can also store anything in them. You could store songs in a queue. If you have a song struct, you could store classes in a queue. You can store floating points, whatever you want, in a queue or a stack. There are lots of other different types as well that we haven't talked about. There's this vector, which we will get into. They've also got a priority queue, which is basically a heap. In fact, under the covers, it's a heap. They've got sets, which we mentioned last week. They've got maps, which are key value pairs, like a hash table. Some maps are done with a tree. Some are done with an actual hash table, et cetera. So there's lots of different types of these containers. Okay? And again, the whole point here that I keep hammering is they will store any type of object. Okay? Questions so far on that? All right. Here's kind of how they work, at least the title for how they work. The standard library classes use this thing called compile time polymorphism. What the heck does that mean? It means that when your program is compiled, the polymorphism means the ability to use any type at all. When your program is compiled, you have a function that says, I can work on any different type. And then you say, I want it to work on integers. The compiler says, OK, I'm going to build a specific type or a specific function that will work on integers. So it doesn't, unlike in Java that does it as you go, it's not, this does it in compile time, so it's very fast. It happens at compile time. It builds an object that allows you to hold any type of, or whatever object, whatever type you want, and it builds it on the go. Okay? And then that container function works specifically on that type. So you tell a queue, here's a, I want you to make me a queue of integers, and it says, fine, I will redo the whole function so that it will just work with integers. And then later in the program, you say, I want a queue that will do floating point values. It does the same thing. It recompiles it to be floating point values. Okay? Questions on that? Polymorphism, not going to be tested. But the idea of it, that you can use lots of types, is the whole point of all this. Okay? All right. So let's talk specifically about this vector class. In fact, we'll spend a good bit of time on this today because there should be some questions about how we will implement this for the actual project, how you can use this in your project. The vector class is just a dynamic array. All right? The bottom line is it's a dynamic array just like the ones we've been using all semester. Right? The deal, it has all the same complexities. Right? If you're going to add a value at the end of the array, it's order 1. If you're going to try to insert in the middle, it's order n, etc. Right? It also has the ability to reference random places in the array, which is good. Right? You need to know randomly maybe where various parts are, so you can do that. But all the details are handled behind the scenes. That's nice. Okay? What's wrong, Susie? Are you? Oh, OK. I was thinking you're looking at me like I'm crazy. All right. So everything handled behind the scenes. Vectors have the ability to do lots of the things that we've already done by hand. Right? If you say, I have a vector and I want to push back, with an underscore there, the value, right? Then it adds the element to the end of the array. Easy enough, right? It's like saying the last value gets the element you're trying to add. Okay? If the vector is full, like capacity, under the covers it says, oh, we need to expand. Call the expand function, expand, copy, rename, blah, blah, blah. Right? It does that all for you. Okay? There's a lot of these different functions. In fact, let me show you where you might want to go online to get to these functions. If we type in C++ vector, the first one that comes up is from c++.com. And it shows you all the different things about vectors here. It explains it. It talks about the properties, gives you some parameters, tells you all the little member types in here. Here's all the little, well, there's the iterators. We'll talk about what that means in a little bit. And then some other functions like the size. Right? The size of the array is how many elements it contains, not the capacity. If you want the capacity, if you happen to care about what the capacity was, there's the capacity. Right? You can tell it to resize. It will do it automatically. But if you say, you know what, I think I'm going to get a lot of words here in a minute, maybe resize, you can tell it to do that. Right? You can reserve a capacity. Right? You can, there's a new function in C++ 11, which is the newest version of C++, which says shrink to fit, which is actually pretty cool. Let's say you're going along in your dynamic array, and you're adding, and then you have to add one more element, but that happens to be at capacity. So you double the size, and then you've got one little element extra there, right? Well, if you do shrink to fit, it goes, oh, OK, I'm just going to grab another chunk of memory this big, and then drag everybody into that, and then give back the other memory. Kind of nice. Margaret?
Will it get rid of unused memory in the middle of certain array?
Will it get rid of unused memory? So remember how it works. You get the whole piece, and your array is in partially filling that, let's say. Then it gets a whole new piece, copies everybody over, and gives back the whole first piece. So that whole first piece gets given back.
Say if you have an array, you only have elements 1, 5, and 7 being used. Will it shrink it down to
No, it won't shrink things in the middle. No. It doesn't. If you have an element at element 5, by definition, there's one at 4, 3, 2, 1, and 0 as well. Even if you're not using them, they're all there as well. OK? Good. So that's some of them. It also has the operator bracket function, which is really nice because what that means is, this is not going to look so great because the screen's up, but what it means is you can say if you have a song, I actually wrote it up here before, that means the first element in the vector. It's just like an array. Okay? They have overloaded the brackets to say, oh, I get to use this notation. Song, right? 40 is the 39th element in the array, right? Is it that? No, the other way around. 41st element in the array, right? So, but you see how that works? Okay, it's overloaded like that. So there's lots of different functions you can use. We will only talk about a few, but there's a whole bunch in here that allow you. Look, you can also do swap. You can swap some content with another array. You can remove an element from the last part. You can push back, et cetera, et cetera. Clear it. And there's a whole bunch. There's some I don't even understand because I haven't looked at them yet, but it's that. Okay. So we talked about most of these right now already. There's pushback, adds the element. Size gives you the number of elements. Bracket notation lets you do this business. There's also an insert function that says insert at some position. You can't just say insert at position 0 and then the value. You have to have what's called an iterator, which we'll talk about in a minute. It's, the reason they do that is basically so they can do some checks for you, but you have to do what's called its iterator, which makes it a little bit trickier, but not that bad. Okay? Questions on the array yet, or the vector yet? Yes, Evo.
How do you initially declare a vector? Is it where you pound include vector? Okay.
There you go. Right? You do have to do pound include vector. Yep, good point. I forgot about that. You have to do pound include vector like that. But then when you declare a vector, you just say this. Vector, then the type of stuff you want to put in it. Integers, song, structs, whatever you want. And then the name of the variable, just like anything else. And it's just like the q the way we did it. Before we had q int the letter q. And that was said, give me a q of integers. Now this is saying, give me a vector of whatever integers or whatever. Okay? Example here, a vector made of strings called lyrics, which I think may be kind of important for this current project. Right? A vector of strings called lyrics. Okay? Any other questions before we keep going? Yes. Jason. You can specify the capacity. I believe what you do is in the constructor, instead of just saying variable, you put a parenthesis and then the number you want. I think that's how you do it. Let me see if it's off the top of my head here, or if it's right here. Constructor. Let's look. We click on it. Empty constructor, fill constructor, constructs a container with n elements. There you go. Well, actually, this is just each element is a copy of value. Oh, I didn't know you could do that. Well, that's kind of cool.
Well, I mean, you can declare it and then say reserve, because whenever it's declared, it's automatically declared as with 0 spots. Yeah.
Right, but in this case, if you wanted to fill it all with nulls or something, you could do it this way, and then it would create it with that many spots and then fill it with nulls. But yeah. So anyway, or you could do the reserve, or you could use reserve.
What would be the syntax then to answer that question?
I believe it would be this. It would be vector string lyrics parenthesis the number you want. Although
No, you need a val in there.
no, the number would be the value, right?
So like if you want a 10, it would just put 10.
It would put 10 blank strings, basically 10 empty strings. Yeah, 10 strings of empty strings, basically. Yeah. I don't know that you'd necessarily want to use that, because it's pretty efficient about making it bigger. And by the way, you don't necessarily know how many songs there are going to be, for instance, or how many words in the lyrics. Now, somebody else asked me earlier, she said, hey, if I know that on average songs have about 30 words in them, can I do it that way? Sure. If you think on average, if on average you've got about 30, then you can do that. Or you can reserve that capacity. You can do it that way. Okay? All right, so that's how we declare a vector. How do you actually use it? So let's say we have a struct called a song, maybe useful this week, and it has a string for an artist name, and then a string for a title of the song, and then it has a vector full of strings of lyrics. Right? This is your dynamic array. This is not a bad struct to have for your songs. It's got everything you need for the song. Now, if you're dealing with like frequencies of words and that sort of thing, different story. But you can do that maybe in another structure, or you can include it in here. But that's up to you. But I think I like this. I like this method right here because it's straight to the point and it tells you what, what's actually in the song: the lyrics, the title, and the artist. Good. All right. You guys are quiet today. All right. Where's Allie? She back here? No. That's why. MIA. How do you use, like, let's say you have a song class, and in the lyrics part, you want to actually push a word on it. You would say lyrics.push_back word. In fact, in that case, you'd have some song name, arrow or dot, lyrics.pushback word. And that takes the next lyric, puts it at the end of takes the next word and puts it at the end of the lyrics. Okay? Again, no need to expand. Yeah?
We need to be careful to pay attention to how vectors actually doing these actions to figure out what order of operations it's using.
What complexity it's using?
Yeah.
No, because if you go back and look at when they build these template classes, they actually say in the definition or in the description of the class what the complexity has to be. In fact, let's see, is this page tell it? I don't know if this.
Whichever part of the
Hang on. Yeah. If you go to push back, it will say that the complexity here is constant for pushback. So it tells you what it is, right? So it has to be guaranteed that it will be on average constant complexity. Okay. Yeah. Now, by the way, so we've been designing these dynamic arrays for months now, and we've been doing linked lists, and we did hash tables and queues and all that, right? The reason we teach you those, of course, is so that you know what they are under the hood. Like that you can actually use them and be able to analyze them and say, oh, I know that a queue has order 1 complexity, but you can only get it off the front, you can only push in the back, because you need to know those things, right? In real life, you're probably not going to go designing your own queue. You get to your first programming job, like some summer, you go to an internship, and they say, okay, here, could you design a song database thing for me? And you go, yeah, okay. First things first, I'm going to create my own dynamic array class, right? They'd probably look at you like, what are you doing? You must have just gotten out of data structures, right? Because they'd be like, good, I'm glad you can do that. Don't waste your time. Use a vector. And there's a number of reasons for that, right? Number one, why would we not want to write our own vector class? Yeah. Takes a while, right? You're not getting paid to write stuff that's already been written, right? What's the other? What's a good one? More space for your own bugs. Yeah, that's a very good one. When you write your own dynamic array class, you don't have a million other people who have looked it over and said it works, right? You've got you, right? And like maybe the other kid sitting next to you, right? And he's not going to know, right? So these standard template libraries have been looked over by millions of people, right? And if there's any bugs, if there ever were any, there's none left now, right? So that's the other point. Another one?
whoever was looking at it probably had like 5+ years of experience on it.
There you go. They've probably got lots of years of experience, and therefore, you ever noticed like, oh, let's say you build a quick sort and it's not as quick as you think, right? Remember, like everybody's like, oh yeah, my quick sort wasn't that quick. It's because you made some little mistake somewhere that did extra work, and that multiplied by the number of the size of the array. It was still quick sort, but it wasn't as efficient. They've got they've been doing this, and they know how to make it perfectly efficient, and people have ground away at this for a long time. Yeah.
It's not standard, right? You may like have different function that is not standard for all.
Okay, so that's true too. You may not have standard functions. You may not have standard functions. Now, there are times where you may want some other function, in which case, well, you could actually dig in and there's ways to overload functions and things yourself, so that you could use your own functions. But yeah, it's not like your functions might not be the ones that are standard for everybody, right? So that's good too. So there's lots of reasons not to do that. You want to spend your time working on stuff that isn't standard. That's kind of the other point. Okay. All right. Back to this for a sec. So you push back the word on your lyrics. That's the next one. Okay. We already said that you can get the first word by doing lyrics 0. You can get the second word by doing lyrics 1. If you use this, this way of getting the lyrics, C++ does not check to see if you've gone too far. You can ask for the 2000th element of a vector in this method, and it will gladly give it to you if there's only one element in the vector. It could cause a seg fault. It could cause some other problem. It will give you garbage data. But you can ask for it. There is another way to do this, which takes more time, which you say, instead of lyrics 0, you say lyrics.at, at, parentheses 0, and then it checks and says, does that one exist? And if it doesn't, it gives you an error. So it's a little better, but it's slower, because it has to do that check. But either way, lyrics.size tells you how many elements are in the array, not the capacity, how many actual elements you've put in there. Okay, that's what the size gives you. Okay. Questions on that? Good. All right, how do you iterate through a vector? In other words, how do you walk your way through a vector? Well, there's a couple different ways to do it. Method number 1 should look very familiar, except maybe for the size underscore t here. Size underscore t is just the size of the pointer that vectors use. Don't worry about the details. Just know that it's an integer that's of the correct size. Okay? Just, yeah.
Yeah, that starts to become really painful if you're like going down. So if you're going like I minus minus and you're starting from like size and going backwards. Size minus size underscore t. When you go negative, it flips over.
Oh, well, right. Size underscore t actually it's actually an unsigned integer is what it is. Okay, so it means that it starts at 0 and goes all the way up to 4 billion. But that's how big it is. So it's an unsigned. You could also make this an unsigned integer. But the point is you need to make it this way, or you'll get a warning. You won't get an error generally, but you'll get a warning anyway. So anyway, make the lyric size equal to the lyrics.size. I got yelled at by Bruce this morning because I had it backwards. Or I had it in here where I put lyrics.size inside the loop here. And Bruce, afterwards, he didn't tell me in the middle of the lecture, although I wish he had. He said, hey, don't call functions in the middle of your loop, because that wastes a lot of time. Set it first, and then use it in the loop. Anyway, live and learn. Now I know. I've been properly chastised. So, well, you know, you want, it's a mistake. OK, so anyway, here's how you walk through it. Size t, like the index equals 0. I is less than the size of the vector, I++. C out lyrics I with the lyrics I being the index, and you're done. That should look very familiar, right? We do that for arrays all the time. It's the exact same pattern. Okay? This is one way to do it. There is arguably a better way that is also a little more painful to understand before you get your head wrapped around it. Okay? It's called using an iterator. An iterator is basically a pointer to, well, it's a pointer that says how to go from one to the next to the next. For vectors, it's easy. You just add one, right? But for maybe if you were trying to iterate through a hash table, which is technically possible, you would not go to the ones that are empty. You just go the first one, then the next one that's not empty, and then the next one that's not empty. Okay, so there are reasons why we use iterators. Vectors are not really the best example of it. But let me show you what an iterator looks for. You don't have to use them, but you will want to start using them in your own code later. Like if you do more C++, you'll want to start using iterators. Okay? Here's what it looks like. All right, bear with me on this one. Yeah, look at it for a sec. It looks a little crazy to begin with. OK, first thing you're doing in here is you're saying this is the type of the thing you're getting. It is going to be a vector of type string, a vector of the whole strings, and it's going to be an iterator. OK, this just means it's an iterator. It's like the class that we're using inside the vector string, OK, or the variable type. Word, instead of an index, we're just going to say it's going to be word. It starts at songlyrics.begin. Well, that's nice. If you're going through the whole array, you start at the beginning, right? Begin is the first element in the array, or in the vector. You go until your word is not, or you go while your word is not equal to the end. The end is not the last value. It's the one. It's basically you can consider it the one after the last one. It's saying I'm already done. So if you get the end itself does not have not have a value associated with it. It's like the size of the vector. You know, we're always going less than 5 if it's 0, 1, 2, 3, 4, right? The size is 5, and we're always going the index less than 5. This is the same idea. You go while the word is not equal to the end. Okay? And then you just increment it like you normally increment things, right? So this is what it looks like here. You've got you got the iterator itself. You've got the first element, you've got the just after the last element, and then you're incrementing it. Incrementing is interesting. For vectors, it's just 1, 1, 1, 1, 1. Well, it's 1, 1, 1 for the type like for an integer type. But let's say you had a structure like a song in here, right? Like not strings, but a song. You would want to go one structure, then jump to the next structure, then jump to the next structure. That calculation is done for you by the compiler. So that's actually kind of nice. And then same thing. You're going to actually see out not the word, like not the bracket notation, but this is a pointer to the word. So you print out, you dereference the pointer, and you print that out. So star word says that's the word that I'm printing out. Yes?
Is the iterator a pointer?
It is a pointer, yeah. The iterator is actually a pointer in this case. Yeah. I know it doesn't look like it, but it is. Well, right. When you can do plus plus on a pointer, and it goes to the next one in the array, right? And in some other structure, it jumps to the next one, whatever definition of next means. And that's kind of the tricky part. The other, what else was I going to say about this? The word plus plus, the word, yeah, you dereference it and print it out like that. Let me show you what it looks like in the program itself. So, there we go. OK, let's see. Let's make this a little bigger here. You don't need to see this here. I showed a couple people earlier what this is. So I have the song structure like this, right? And I'm actually printing it out. Let's see. I believe I print it out here. So there it is. Print song info. Here's the simple counter method. This is the vector method I just showed you. It's exactly the same code. Okay? And what it does is it first prints out the artist, then the title, and then it prints out for each word in there. Oh, I know what I was going to say. Does anybody program in Java and you know of the for each way of going through values? You know for each? This is basically a for each. It says for each value in the vector, do something with it. It's kind of the same idea. Okay? For each word in the lyrics, do something with it. In this case, print it out. And this is what it does here. By the way, I printed these extra little less than and greater than just to show you where the words are broken up here. You don't need to put those in there when you're, but this is like Rick Astley's cry for help, and hold me in your arms, etc., right? My arms keep missing you, whatever that means. I don't know, never going to give you up. Because I've been working on this project for so long, every morning I keep waking up with this song. I've like Rickrolled myself, right? It's really sad. I keep waking up and thinking this song and going, oh, I'm done. I have Rickrolled myself. All right, anyway. So anyway, so that's how these iterators work. Okay? Yes, question?
So is
Jason.
the input benefit of the iterator, or just like whatever next thing is instead of like why do you want to
Yes. Why do you want to use an iterator? Good question. And you're absolutely right. The iterator is generic, right? This whole idea is let's make things more generic. The iterator is a generic way of saying go to the next value. You can also have reverse iterators, right? So you can say, instead of saying you couldn't do this, you couldn't flip this and say start at the end and go to the beginning in this form and do I minus minus. Well, actually, I minus minus would work, I believe. But what you could do instead was say start at the reverse begin iterator, which says plus plus will take you back one, right? So it's a little odd, but there's other ways of using iterators that aren't just easy, like one to one to one to one to one, right? It's a generic way of doing it. Yeah.
So if you're using this to like run through a hash table, plus plus will just bring you the next element.
Yeah, if you're doing it, I'm not certain that the map or the unordered map has an iterator that will let you go through each one. But if you did, it would go from one to the next, skipping all the places that are empty. That's the point of the iterator. Yeah, it does all that under the covers for you. And you couldn't do that with just you couldn't do it as easily with just an index. And you don't even get access to an index in the, you don't get access to the index in a map. Yeah. OK. Questions on this? Iterating through a loop? Again, you don't have to use this iterator business, but you'll need to start using it as you get more and more experience in C++. Yeah?
So here is this another instance of where we wouldn't want to call a function in the for loop.
Yes. Now, that's a good point. Well, all right, that's a good question. Like, are you saying, hey, you did call this function and that function? This is the way it's done. I believe this is not, well, it is a function, but I don't think it actually has to calculate anything. I'm not sure. But I've seen it like this many times. So that's a good, I'll have to check and see if that's a proper, this is the way I've seen it all the time. So I think what happens is, because these are iterator, you can actually, the compiler can say, oh, I know the number for that now, boom, and put it in there. Versus the other way, it doesn't know what your function is, so it won't be able to, like the size function. It can't figure out the size necessarily. But that's a very good question. I'll have to find out the answer to that. Yeah?
So when you're using that method for the vector class, you have to pass it.
You do have to pass it for the iterator, yes. You mean the insert method or this method? Yeah, it was insert. You have to pass an iterator, which you would generally pass. You can pass lyrics begin plus 12. You can't pass 12, because that's not an iterator. But lyrics begin is an iterator, and it can add 12 to itself and know that that's 12 away from the beginning. It happens that the iterator's lyrics begin points to the first one, which is index 0. So it seems like, oh, why don't you just add, it's just going to add 12. But remember, it's got to be an iterator. So it's a little more detailed. It's like a little more detailed than just passing the number. Yeah, good. Yeah.
So what's going on underneath the covers? It seems like something's going on weird between what we generally understand as adding a number to something versus us adding a number to a pointer here. So are the spots in memory one next to each other, and we're just?
Yeah, that's a good question. That is a great question for Comp 40. But yeah, whenever we say index plus plus, okay, the index is getting one is getting added to the index. It's just an integer. The integer goes from 1 to 2 to 3 to 4 to 5, right? The array notation under the covers is doing some of that fancy saying it's not just 1, because your integer is 8 bytes long, right? So you're not jumping 1 memory location, you're jumping 8 memory locations, right? And it knows that based on the fact that it's an array. So there's more going on under the covers than just saying 1 to 1 to 1 to 1 to 1. Yeah, good question. Good question. All right, let's move on to the next part here. Oh, and by the way, this is when you dereference the iterator. It's just a pointer, so you're saying, give me what it's pointing to. Okay. All right, where else might you use a vector? In the song search assignment. Well, does this look familiar? Right? Vector of song pointers, songs. Can we store song pointers in a vector? Absolutely, it's generic, so we can do that. Cool, right? Push back the song. If you are keeping, let's say you want to, I don't know, keep a list of 10 songs, say that contain a certain word, right? You would do this sort of thing. You could say, I've got a vector of my songs, and I've got 10 of them in there. You also are probably going to want to keep the frequency of that word, so we're going to expand on this just a little bit. Okay?
Being just 10 and keeping it from expanding any more than that?
You keep track of the size. So you say if the size is greater than 10, I need to either kick the new song out or put it and kick some other song out. But you have to keep track of that. Yeah. Okay? All right. Where else might you use a vector star? Anybody thinking of doing a try? I've talked to a number of people doing tries, right? Yeah, question.
But, so in lab with that practice of using try with that, do like the math practice and not have to iterate the whole thing?
Yep, good question. So the comment, Jason's comment is, look, when we did tries in class, we were able to have the index of the character based on the fact that the characters are A through Z and inline in the ASCII character set, blah, 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 right? Well, two problems with that now. Problem number one, we're not just the characters. There's also digits 0 through 9, which aren't right next to A through Z, as it turns out. It's kind of too bad, right? But the other one is that really when you did that, you had to have 36 nodes, or well, 26 nodes immediately for every child, or for the children of every node. In this way, we're going to save some space, actually. Because what you're going to do here is you're going to say a vector of node pointers, and it's going to start out with nobody in it. It's going to have a capacity of maybe 7 to 10, or whatever their initial capacity is. But it's not going to have anybody else in it, right? So you're going to save some memory there. Yes, you'll take a little more time to look through the vector, but it's not that hard to do. Okay? So anyway, you might do it for tries. If you're doing a try, you will have the child nodes, the nodes of the children being a vector. And then you push back the next new child node, and then you have to search through the children to find it. Not a bad idea if you're thinking of doing tries for this. On Piazza, I put a link to how to do that. Or I put a link to a web page that does this method. Okay, so if you're having trouble doing that, you can look at that. Voids having to have 36 children for each node. Okay. Anybody, how many people are thinking of doing tries? About a third of you? OK. That's cool. That's great. I look forward to seeing how that works. I think it'll be great. OK, so that's what you would do for tries. Good place to use it there. All right. What if you want to sort a list of songs by the frequency of the word they contain? You guys built all these sorting algorithms, right? And if you want to sort them, you can go through each one by one, and you can do an insertion sort or a quick sort. I would not do a quick sort on a list of just 10, but maybe an insertion sort or a selection sort or something like that, or a relatively easy one. But you could do this. You could keep a structure of something called like song with frequencies, which has a song in it, which itself is a structure. Actually, it has a song pointer in it, which is itself a structure. And it also has the frequency of the number of times that word appears in that song. That makes sense? If you do that, then you can have a vector of song with freaks called song with freaks. Right? Right? And you could actually have this and then sort these guys by the frequency. Now, this is a little more in-depth than some of you will care about, but guess what? There is a sort function built into C++. Part of the standard library has a quicksort, it's normally built with a quicksort, in it. It will do the sorting for you. Instead of you trying to do that sort your own, which you did last week for the assignment, you're done with sorts, right? You've been down that road. You can use the standard sort class if you want. Let me show you how it's done. First of all, in order to have anything sorted, you have to know what you're sorting against, like what you're comparing, right? That's the whole point. You have to provide a less than operator. It's very easy to do. I will show you how to do it. It's an operator overload. Very easy to do. You provide that overload less than, and you can actually get the sort ascending like this. That's caveat number 2. The default sort is ascending, not descending. Okay, so what that means is if you were trying to get the top 10 songs, well, the last song will be 12. That's the top one, and then the next top one and next top one. 2 ways to handle this. Way number 1, use a greater than function, which is possible. You have to also overload the greater than operator. That's not that hard either. Or you could sort it ascending and then reverse the string. There happens to be a vector reverse function as well that will do the reversing for you, right? Probably use a stack inside or something. right here. Let's see. Reverse is, there it is, right? No, that's reserve. Where did it go? I knew there was, well, maybe there isn't one. I thought there was. What's that? Did I thought I saw it too. No, maybe it was just reserve. Well, no, there's a reverse iterator, so you could reverse through it and do it that way. But anyway, the point is you can get a descending sorted list if you want to. It's not that hard either. Okay? Let me show you the code. And all these examples for today's lecture are online. So if you are having trouble starting the assignment, like let's say you're not exactly sure how to get going on it, you can use the code I just posted online today to like jumpstart yourself, right? It will get the words into the songs for you. It will do all that. So if you're having trouble, feel free to use that. Okay, I have no problem with you using that. But here's another thing that's online here is the example for song with freak, right? Okay, you have to overload the less than operator. Watch how easy it is to do. Boolean, when you can compare two values, it's going to be a Boolean return value, true or false. The operator less than is what you're overloading. This is like boilerplate. In other words, this happens in every one of these overload things. You've got const, you've got the name of the class, you've got the left-hand side with a little reference, you've got const right-hand side. You're basically saying, right, compare the left-hand side to the right-hand side with the less than operator. That's all you're doing. And then look what you do. If the left-hand side is less than, if the left-hand side frequency is less than the right-hand side frequency, return true. Otherwise, return false. Very simple, right? Yeah, question. You can't. That's what references kind of do, passing by value. Yeah, references real. They allow you to get at the actual value itself. Yes. Yep. So this is your overloaded function, right? How do you do the sort? Boom. You say sort song with freaks begin. It's an iterator, going all the way up to song with freaks end, also the iterator. And when you do this, once you run that, afterwards, the song vector will be sorted by frequency, ascending, right? Easy. If you do it this way, it's easy. Yeah?
If it's already ascending, could you just read it backwards?
If it's ascending, you can read it backwards, sure. Yep, absolutely. It is sorted, so however you want to read it in whichever direction you can. It's good, yeah. Okay, all right. Hopefully this will help some of you guys out as far as like doing some of your sorting if you're trying to do that, the assignment. Yeah? Say you had a vector that's a hash table, yes.
And you wanted to insert, each word, each one of these 40 million words into this long hash table.
Yep. You want to insert the words into the hash table, yep.
So then what do you modify? Like what's the ever changing?
It is ever changing, right. You're probably not going to have the hash function, you're probably not going to insert into a vector for this one. You would probably want to use just a dynamic array under the, like if you're building your own hash function. Okay, you would probably want to do that. But how are you going to mod it? You're going to mod it by the width of the capacity of the array, right? And then when you get to a load factor that's big enough, you do have to expand the array. How do you expand it? You rehash everybody to the new array, right? So it is kind of painful, but you have to do it that way. Okay, yeah. Question, Jason?
Yeah, so for the hash table, you want to check the load factor and not like the capacity or the count or anything. You want to like have like a specific load factor.
Yes, you want to have a specific load factor. In my own testing, it was really fast if I used a load factor of 0.2, as you can imagine. 0.8 was really slow, as it turns out. Who knew? I thought it was going to be faster. So I would pick somewhere in the middle there, right? And you could pick, you could go as low as 0.2 if you want. Manvi. The vector would be part of that song struct, yes. Yeah, well, I don't want to go all the way back there, but I think it's in there. It shows it in there as part of the song struct. Yep. Yep. It can be accessed just like any other class has an element. Song name, period, lyrics. Yep. Good. Yeah.
There was a function that inserted the capacity of the vector.
Yes.
Is that just random every time then? Like what is the capacity?
No, it's not random. So under the covers, they're smart enough about it, and I taught you, I think, what the smart way of doing it is, right? You start with a relatively small capacity, and then every time you need to expand, you double it, right? So you double it each time. That's the way they do it, too. Yeah, good. Question, please.
What, when you were testing your hash table, what collision, like how were you handling collision?
I was handling collisions with a linear probe, yep, which I thought was easiest to do. It made the most sense. It was easiest to do, and it was relatively fast. Yep. I was talking to some other people today about doing a chaining with a vector. If you're going, instead of chaining with a linked list, chain with a vector. You might as well. Same idea. Yeah, Susie.
Is Mixart going to be the fastest? It's Mixart because there's only 10 items.
Oh, good question. Is this going to be that fast? It may be a little slower, yeah. Now, actually, you know what? You know what? They're smart.
Do they put insertion sort for small?
They put insertion sort for small ones, yeah. Yeah, I think they're smart like that. Yeah, so good question. Yeah, Charles.
I have a silly question, but
Silly question, yeah.
not silly, but how do you calculate the load factor? Because they're both, like, your sizes and capacities are integers.
Yeah, good question. You have to overload, or you have to cast one of them. So you can do this. You have to cast to a float. Yeah. So if you have a let's say items, right? You're going to do the number of items divided by the capacity or the table size, right? You would cast it to float table size, right? And when that will return a float. So yeah, good idea. Yeah, good point. If you try to divide just the integers, it would give you an integer. It's always going to be 0. Yeah. Yeah, good point. OK. Other questions? Good questions. All right. So this, if you want to see the whole example, it's online. OK. All right. So now we are finally to the part where it starts to, I think, get kind of interesting. How is it possible for a class to accept any type? Right? I mean, we talk about this. And we say, oh, well, let's put an int in there. We'll put a struct in there, or whatever. How is it actually doing that? I said there was this compile time polymorphism. But what does that actually, like, how does it actually work, right? Well, generic programming, right, is this really powerful feature of C++, OK? And what you use is these things called templates. There's a reason it's called the standard template library, because they use templates to do it, right? So the standard template library uses these things called templates. We are going to build your first template, OK, and see how this actually works. OK. This is not your first C++ template. This is like in a we'll get there. Let's say you want to create a calculator program, a really simple one that adds and multiplies two numbers together. OK, pretty simple. You could do this. You could call the class calc or calc1. You could have a multiply function that takes an integer and another integer, multiplies them together, and returns an integer. You could do an add function, same thing. And then the actual functions themselves are as follows. Multiply takes x, multiplies by y, and returns it. This is a very simple function, right? Same thing for add. All right, it works. 1 plus 2 gives you 3. 2 times 3 gives you, when you do add 1 times 2, it gives you 3. When you do multiply 2 times 3, it gives you 6. Ta-da. What's the problem with this? And it's not a problem with integers, but it's actually kind of similar to what Charlie's silly question was earlier. Can I put floating point values in here? No, right? It takes an integer and an integer. You'll get a warning if you try to put a floating point. It would probably let you. But you would definitely get back an integer, right? If you did 1.2 times 2.3, you would get back 2, right? You would not get back 2.6 or whatever it is, right? Because it would be integers. So there's your problem. All right, it's not generic. It's very specific. If you wanted to make this for floats, you could go back and change all your code here. And everywhere you see an int, make it a float, and that would work. But that's a lot of work. Why bother doing that when you could make it generic using these templates? Here's how you do it. Here's how you do it. There we go. All right. First, you say, I'm making a template. Fair enough. Then you say, I'm going to have a type name. Sometimes you will see this as class, but they've changed it to type name now. I will have a type name, and that t is just a variable right now. It's a variable for the type that you are going to use. Later, that will get added in when you choose a type. So you ready for this? Multiply takes an x and a y, both of type t, and returns type t. Same thing is true for add. Takes type t, and what it does is it just does x times y and returns the same thing, returns that type t. Now it's generic. That's actually all there is to it, right? In main, you say calc2 of floats, calculator 2. C out 1.5 plus 2.7, that works. And it works for 2.2 times 3.3 because you've made it now a calculator for floats. Okay? This won't work for a float and an int. You'd have to do another template for that, right? But you could also do, people have done that as well, where they have two types up here, right? Or rather, I guess it would be two types here somehow. So you can make it even more generic if you want to. Okay? But that's how you do it. Does this work? It works. We'd solve for numbers. Is it generic now? I mean, can we add any type in there and add and multiply those types? Sure. Does it work for strings? I don't know. If you add two strings together, is that a pretty well-defined function? What happens when you add two strings together? You concatenate them, right? So if I say string add, calculator strings add a, b, c, and d. By the way, I've made a calculator for strings here. A, b, c, and d, e, f. Right? It will concatenate them, and it will print out a, b, c, d, e, f. If I tried to write the following, a, b, c times d, e, f, and multiply a, b, c, and d, e, f, the compiler says, what are you talking about? Right? It says, I don't know what it means to multiply two strings together. Right? It says, I don't know what that means. What do you do when you multiply two strings together, right? What it means to the compiler is that the times operator is not actually defined for strings. Could we define it for strings? Why not? What did we do 2 slides ago that the same sort of idea about this? Operator overloading, right? So you could overload times for this. What we need to do is we need to figure out what does it mean to multiply two strings together, right? You get to pick that. You could say multiplying two strings always returns, I don't know, always returns cats are fun. Whatever, right? It just you define it, right? It's completely up to you. Here's how I'm going to define it, right? I'm going to say that to multiply two strings means we're going to interleave them. Why not, right? You guys have seen this sort of thing before, by the way. Well, maybe you have. Those of you who've taken physics, if you've taken enough physics, you will have talked about, or calculus, I guess, in general, talked about, what's that? Cross products or dot products, right? For a dot product, I don't know if you remember how a dot product works, but if you've got two vectors, and they've got 3 components each, the dot product is do the first one times the first one, and then the second one times the second one, and the third one times the third one, and then add them all together, and then that's your dot product. It's kind of the same idea here, right? I'm just going to interleave these strings. And by the way, I just made this up. That's what my definition of times is for this. So in this case, ABC times DEF is A, D, B, E, C, F, right? A, D, B, E, C, F. Okay. Well, great. Now that we've got a definition, let's overload the multiplication. Looks bigger than it looks bigger than it is, really. We're going to overload operator star. Remember all this boilerplate? Const string and left-hand side, const string right-hand side, same thing. We're going to return a string, and this is just saying go through the string as many times as the longest one. And if you get to a point where one string is longer, just put the rest of that string at the end, the longer one. Okay, that's all this is doing. You can look at this like on your own if you want, but that's all it's doing. And then it returns the string at the end that we've just created. Okay. Does it work? it does work. If I multiply this times this, and by the way, this, there's a space there, and there's a space before the ERTCD. What does that actually print out? What is it? A secret code, right? Prints out a secret code. This is for, so let's say that, let's say that Sam and I have started a secret spy company, right? And we both want to, we both need to take, we need to get a message from here to the spy headquarters, and but we don't want it, we want it to be so secure that if one of us doesn't make it, nobody can know what the secret code is, right? And we go in different directions, right? And then finally we meet up at the secret spy headquarters somewhere, and we use this calculator thing to multiply our two strings together, and we get the secret code that tells us how to destroy the communists, right? Okay, so so that's that's the kind of thing you could do. You could actually overload it to actually get there. Okay, real life experiences. When are we starting our company? Our super secret spy company? My employer wouldn't. Well, maybe we'd be working for my employer. I don't know. All right. So anyway, point is you can redefine this as you want, but this is kind of neat now. Our calculator or our calc2 template function actually enables us to do any type in there. As long as you define times, you could have structs multiplied towards each other. Maybe it means that you're multiplying individual parts of it, or you could define a dot product or a cross product very easily with this type of thing for different types of numbers. Kind of neat. Okay. All right. C++ templates are pretty powerful, right? You can find lots of these generic programming techniques in other languages. Java, we talked about, Scheme has it, Python, some of these other functional languages all have these ideas. You guys will probably not write many templates, right? You probably won't do that many templates. I mean, it's one of those things where if you're building a class that's going to need to be used by many people, you might, or many different types of objects, you might want to do that. But the idea is you will use templates even more often. Yeah?
In the previous example, if we had forgotten to overload our times operator,
Yes.
what would the error of the compiler?
Oh, yeah, it would have been some error. You'd be like, I have no idea what that means.
It wouldn't be like, no operator for type string.
It might be. What it would probably say is this big, long error message that has like left-hand side and right-hand side, not defined, and somewhere in there there'd be a star, and it's a little bit cryptic. Clang gives better error messages than G++, but it's definitely templates have a bad reputation for giving poor error messages when you screw up. Yeah, but that's part of the complexity of them, unfortunately. By the way, the template compiler is really a whole separate compiler from the C++ compiler. It has to take your template, take the object you're trying to shove in there, and compile the C++ code that then gets compiled. So it's actually pretty intense. Like it's like a big deal to get the template library, the template compiler part correct. So pretty intense. Okay. All right. So as I said, most of the time you guys won't be writing these things. You'll be using them a lot, though, in the standard template library. Okay? And there's a bunch of references up here. There's an Idiot's Guide to Templates. There's generic programming, et cetera, et cetera. Any questions? No? All right. We're a little early today, too. I will stick around here if you want to talk about your projects at 4:30. Yeah, it is actually at 4:30. I'm going back to do actual office hours. So we'll do that. Any other questions? Awesome.